The worst news in the history of our species is probably sealed inside a metal tube lying on the surface of Mars right now. A rover drilled it out of a dry riverbed 2 summers ago. Last September, the journal Nature reported that the core inside contains what scientists carefully call a potential biosignature. Almost everyone read that as the best news imaginable. There is a published argument, standing unbroken for nearly 30 years, that says it is the worst. Not because anything out there could hurt you, because of what its existence would say about how much time you have. If that lands wrong in your chest, hit like and subscribe, because this gets worse before it gets clear. And tell me in the comments where you are and what time it is where you're sitting. I want to know who's awake for this one. Settle in. We're going down into that riverbed, and we are not coming back up for a while. Let me hand you the single piece of this that keeps a certain kind of scientist awake. Then we'll back up and build the rest properly. The rock is called Jezero Falls. Its surface is covered in pale rings with dark borders, each one about the width of a grain of rice. The people on the mission started calling them leopard spots because that is what they look like. Scattered between them are smaller black specks they nicknamed poppy seeds. Those rings formed exactly where they sit. Nothing washed them in. Something chemical happened inside that mud, spread outward from a centre, and stopped when it ran out of fuel. In the pale core of each ring sits a mineral called greigite. It's an iron sulfide. To build it, you need sulfate and organic carbon to react with one another. Now the part that matters, and I want to attribute it carefully, because it carries most of the weight in this story. According to the team that published the find, that reaction is desperately slow at the temperature of a cold lake bed. So slow that nobody observes it happening in natural environments on Earth. Where we do watch it happen is in exactly one setting, when something alive is driving it, on purpose, to pull energy out of its surroundings. One other route exists. Cook sulfate and organic matter together at temperatures well above boiling, and the reaction will run. The mission team went looking hard for any sign that these rocks had ever been heated like that. Within the limits of what a rover can measure, they found nothing. So there is a rock on another planet holding the wreckage of a chemical reaction. As far as we currently know, nothing but life performs that reaction in the cold. None of that is proof, and I want to be blunt, because the scientists who found it are blunt. What we have is a wet footprint on a bathroom floor. Somebody walked past, or a towel slid off the rail. From the footprint alone, you cannot tell. And the footprint is not the frightening part of this story. Now let me build the world that this rock is about to take apart. Go outside tonight, anywhere on Earth, and nearly every point of light you can pick out is a star inside our own galaxy. A few are planets in our own system. One faint smudge, if your sky is dark enough, is an entire separate galaxy. There are a few 100 billion stars in ours. For almost the whole span of human existence, we had no idea whether a single one of them had planets of its own. Then, 3 decades ago, we found one. Then a handful. Then the floodgates opened. Last September, NASA's official tally of confirmed worlds beyond our solar system crossed 6,000. Astronomers now think essentially every star you can see with your eyes has at least one planet going around it. That quietly rewrites the arithmetic of loneliness, and it is hard to feel in your body. Planets are not rare. Planets are the default setting of the universe. Our own neighbourhood warmed up too. Mars used to be wet, rivers cutting through highlands, standing lakes, weather. Some researchers argue for a whole ocean in the northern lowlands, though that one is still fought over. Under the cracked ice of Saturn's little moon Enceladus, there is a salty ocean venting into space through fractures at the South Pole. Under the ice of Jupiter's moon Europa, there is very likely more liquid water than in every ocean on Earth combined. So the mood in this field, for about 50 years, has been a kind of patient confidence. The ingredients are everywhere. The real estate is everywhere. Finding a second example of life is a matter of instruments, funding, and stubbornness. And when it happens, we all assume it will be the finest day our species has ever had. Picture that day. Somebody stands at a podium. There's a slide with a spectrum on it, or a photograph of a rock slice under a microscope. It is the least dramatic image you have ever seen. Teachers wheel televisions into classrooms. People pull over on the highway to listen. That night, everybody looks up differently, because the sky just stopped being empty. Every space agency on Earth is currently building towards some version of that moment. Nothing our species has ever attempted is more hopeful. 3 small things before we go on. They will seem unrelated, keep them anyway. The rover that drilled Jezero Falls carries 38 sample tubes. Most of them are full now, sitting on the Martian surface. The 25th one has a name. The name is Sapphire Canyon. There are pieces of Mars on Earth right now. Around 400 of them, catalogued, sitting in museum drawers and university basements. Nobody went and collected them. They arrived on their own. And in the summer of 1983, a physicist gave a talk in London, a meeting of the Royal Society at the end of a very long day. Stephen Hawking was in the room. So was a Nobel laureate. The cosmologist Paul Davies was there, and he still remembers it. The speaker ran many minutes over time. His slides, Davies says, were incomprehensible. What Davies remembers thinking was, whatever is this all about? Nobody sitting in that room understood that they had just been handed the outline of the worst available explanation for the silence overhead. To understand why a rock might be a catastrophe, you have to go back to a joke about garbage cans. Summer of 1950, Los Alamos, New Mexico. The Soviets have just tested their first atomic bomb, and the laboratory is racing towards something worse. 4 physicists walk across the grounds toward lunch at Fuller Lodge. They're talking about flying saucers, which are all over the newspapers that year. One of them, Emil Konopinski, brings up a cartoon he had seen in the New Yorker. Garbage cans had been disappearing around the city, and the cartoonist had drawn little aliens carrying them up into a saucer. That's the level of the conversation. 4 of the sharpest minds of the century, laughing about stolen trash cans. They sit down. The talk moves on to other things. Then, out of nowhere, Enrico Fermi says it. Where is everybody? Edward Teller remembered that the whole table burst out laughing, and the reason they laughed is the interesting part. Nobody had to ask what Fermi meant. The question came out of a clear blue sky in the middle of an unrelated conversation. Every person at that table understood instantly that he was talking about life beyond Earth. That tells you how obvious the problem becomes once you have seen it. Our galaxy has been here for more than 13 billion years. Crossing it, even in slow ships, takes something closer to 100 million years. Anyone who started before us has had room to spread everywhere, many times over. So the sky should be crowded. It looks dead instead. Fermi never published a word about it. He died 4 years later. The story survived around Los Alamos as a kind of local legend. Somebody finally wrote it down decades afterward by mailing letters to the men who'd been at that table. 76 years after that lunch, with orbiting telescopes and radio arrays and thousands of confirmed worlds on the books, we still cannot answer him. We solved the structure of DNA, we split the atom, we photographed the shadow of a black hole. A question somebody blurted out over soup is still open. We did try to answer it directly once. It did not go the way anybody expected. The 20th of July, 1976. 7 years to the day after Apollo 11 touched down on the moon, a NASA lander called Viking 1 settles onto a rusty plain on Mars. A second lander comes down 6 weeks later on the far side of the planet. These were not geology missions. Viking carried instruments built for one purpose, which was to find out whether anything on Mars was alive. Nothing like them has flown since. One experiment belonged to an engineer named Gilbert Levin, and his idea was elegant. Scoop up Martian soil, drip in a nutrient broth tagged with radioactive carbon. Watch. If anything in that dirt eats the broth, it will breathe out radioactive gas, and the detector will see it. Metabolism, caught in the act. On the 30th of July, the first results came down. In Levin's own account of that morning, the amazing thing was that they came back positive. The curve climbed. It looked like soil samples from Earth. So they ran controls. They heated a sample to sterilize it, and the response vanished. Exactly as it should if something living had just been killed. Then they ran the whole thing again on the second lander and got the same answer. 4 positive results, 5 separate controls, 2 spacecraft nowhere near each other. Then a different instrument on the same lander went looking for organic molecules in the soil and found nothing at all. No organics meant no biology. And NASA concluded that the labeled release experiment had been fooled by strange Martian chemistry. Reactive minerals in the dirt, chewing up the broth with no help from life. Most scientists agreed then. Most still do. Hold 2 facts side by side anyway. Levin never accepted it. He argued for the biological reading of his own data for the rest of his life. He died in July of 2021 at 97 years old, still arguing. And this one deserves a moment of quiet. When you run an experiment and get a positive result, the thing you are supposed to do next is run it again. Since 1976, not one NASA mission to Mars has carried an instrument built specifically to test for life. Later rovers hunt for organic molecules and habitable conditions, which is a related question rather than the same one. Nobody has repeated the experiment of offering Martian soil a meal and watching what happens. We got a positive, then we spent half a century not repeating the test. This month, that half century is exactly complete. The situation has moved since then, and not in the direction that closes the case. We now know Martian soil is loaded with perchlorates. Those salts would incinerate organic molecules the instant a sample was heated. That explains rather neatly why the organics detector came up empty. It does not, by itself, explain the shape of Levin's curves. Researchers at NASA's own Ames Research Center published a paper revisiting the Viking biology experiments and concluded, in effect, that the file deserves to be reopened. The most careful sentence anybody can say about that soil is the one nobody enjoys saying. We do not know what happened in it. 20 years later, we thought we finally had it. That story is worth telling properly because it shows you exactly how this field breaks your heart. August 1996. A grey rock the size of a potato, picked up off Antarctic ice a decade earlier and left in a drawer. It carries the name of the place it was found, Allen Hills. Early in the 90s, somebody worked out that it had come from Mars. Then a team led by David Mackay at Johnson Space Center published a paper in Science claiming the rock held the remains of Martian microbes. Tiny worm-like shapes in the carbonate, chains of magnetite crystals of the kind certain bacteria build, organic compounds sitting in the right places. The President of the United States stood on the White House lawn and talked about it. NASA's Mars program, which had been quietly dying, was resuscitated overnight. The agency founded an entire institute for astrobiology on the strength of one rock. Then it came apart. A team led by John Bradley looked again at those magnetite crystals. They had grown, locked into the structure of the surrounding carbonate. Crystals only grow that way at temperatures far too high for anything to be alive in. The worm-like shapes turned out to be smaller than any free-living organism we know of. Some may have been artifacts of the metal coating used to image them. Mackay published a rebuttal in the same issue of Nature. Bradley's own verdict on where this was heading was blunt. Unless the Houston team conceded, he said, the debate would never die. He was right. It never has. One detail from that rock survived every round of the fight, and it has nothing to do with fossils. Researchers measured the magnetism locked inside it and reconstructed the temperature history of its interior. That rock was blasted off Mars by an impact, drifted through space for 16 million years, and slammed into Antarctica. Through all of it, the inside never got hotter than a warm bath. Anything living in there would have survived the trip. Set that beside the other 2 things I asked you to keep. Which brings us back to a physicist running over time in London. Brandon Carter had noticed something that should not be there. It takes a particular kind of mind to be disturbed by a coincidence. The sun burns steadily for roughly 10 billion years before it swells and cooks this planet. Life on Earth took roughly 4.5 billion years to produce something capable of asking questions about the sun. Those two numbers land almost on top of each other. Why should they? One is set by nuclear physics in the core of a star. The other is set by mutation rates and mass extinctions and the chemistry of seawater. They have nothing to do with one another. You would expect them to differ by a factor of 1,000 in either direction. Carter walked through the possibilities. Maybe intelligence usually appears fast, in a few 100 million years, and Earth happened to be slow. No obvious reason for that. Maybe the two clocks really are linked by something nobody has thought of. Also no reason. Or the third option. Maybe intelligence usually takes far longer than a star's lifetime to appear, and almost everywhere it never gets the chance at all. In that case, the only planets where anybody is around to notice the coincidence are the freak cases that squeaked through just before the lights went out. You live on one of them, right now. Roughly halfway through the sun's stable life, on a world that will be sterilized long before it stops being lit. To make that work, Carter said, our history must contain steps that were wildly improbable. Hard steps. Not difficult in the sense of requiring effort. Improbable in the sense of a lock that falls open by accident. He estimated there could be at most 1 or 2 of them. He never said which ones. For 42 years afterward, nobody else could say either. In 1998, an economist named Hanson took that arithmetic and gave it teeth. He teaches at George Mason University now. Back then he was a newly minted doctorate, publishing an essay on his own webpage. He called it The Great Filter, and he wrote it up under a title that reads like a warning label. The Great Filter. Are we almost past it? His logic runs like this. Take dead matter and follow the road all the way to a civilization spreading across a galaxy. Bright enough to be seen from millions of light years away. That road has stages. A habitable world. Molecules that copy themselves. Simple cells. Complex cells. Bodies made of many cells. Tool-using minds. Then the leap outward. Space near us looks dead, so somewhere along that road there must be at least one stage that is nearly impossible. Unlikely enough that with billions upon billions of rolls of the dice, everything around us came up empty. Think of a relay race where you cannot see the runners ahead of you. All you know is that no baton has ever reached the finish line, not once, in the entire history of the sport. That tells you one of the handoffs is nearly impossible. It does not tell you whether that handoff is behind you or in your hands right now. There is a barrier, that much is forced on us by what we see. The only open question is where you and I are standing relative to it. Which is why Hanson wrote that evidence of extraterrestrials would be bad news. Valuable, he said, but bad. 10 years later, a philosopher at Oxford named Nick Bostrom took that sentence and made it impossible to look away from. He published it in MIT Technology Review, and he did not hedge. He wrote that he hoped our Mars probes would find nothing. Dead rocks and lifeless sands, he said, would lift his spirit. Then he laid out the ladder. Simple extinct microbes on Mars would be bad. Something more complex, something like the remains of a trilobite, would be very bad. The more advanced the fossil, the worse the news. Because every rung we find out there is a rung that clearly was not the barrier. Every step Mars cleared without our help is a step crossed off the list of things that might have saved us. For a quarter of a century this stayed an argument on paper, something to chew on at 2 a.m. There was nothing to test it against because there was nothing in the tube. Until July of 2024. The rover was on its way out of the crater when it happened. Perseverance had already done the job it was sent to do. It landed on the floor of Jezero Crater and examined the lava that paved it. From there, it drove up onto the delta, where an ancient river once dumped its sediment into a standing lake. From there, it worked out to the margin. The plan was to climb the crater rim and start a new chapter. On the way, there was a river channel to cross, Neretva Vallis, a quarter of a mile wide, carved by water pouring into the crater a very long time ago. Along the walls of that channel, a band of pale, layered rock was showing through. They called it Bright Angel. Nobody expected much from it. Everyone expected coarse sediment, because that is what fast water leaves behind, sand and gravel. Mud gets carried past and dropped far out in the lake. Bright Angel turned out to be the finest grained mudstone of the entire mission. Silt settled slowly in a river channel where silt should not settle. The best current explanation is that something dammed the channel, possibly a landslide. The water behind it went still, and the mud came down out of the water column grain by grain, which means the sediment there had time. Time is exactly what you need if you want to trap and shelter delicate organic molecules for 3.5 billion years. The rock was strange chemically as well. Everything sampled lower down in the delta had one character. This had another. It was deeply oxidized, rusty all the way through. It had also been stripped of its magnesium and calcium. Rock ends up like that when rain runs through it somewhere else for a long time, and the leftovers wash downhill. Something about the climate around that crater had changed, and changed fast. On the 21st of July, the rover parked in front of a slab about the size of a coffee table and looked closely. The poppy seeds came into focus first. Black specks, roughly as thick as 2 sheets of paper stacked together. Then the leopard spots. Bigger, pale centers inside dark rims, standing out against red mud like ink dropped onto rust. And Sherlock, the instrument built to hunt for organics, picked up a spectral signature of complex organic carbon. Densest exactly where the spots were densest. Now, what that combination means? What the rover was looking at is a battery that ran itself flat in the mud and then turned to stone. Rust is iron that has given away electrons. Organic matter is carbon with electrons to spare. Put the two together in wet sediment and the electrons start moving. The iron gets reduced, changes state, and joins with phosphorus in the mud to precipitate a mineral called vivianite. Those are your poppy seeds, and that is the dark rim of every leopard spot. In the larger spots, the reaction had more fuel. It kept marching outward, bleaching red iron out of the rock as it went. Eventually, there was no iron left to work with, so the process reached for the next thing available, which was sulfate dissolved in the mud. That reaction makes reduced sulfur. The sulfur grabs iron, and you get greigite sitting in the pale core. A sequence of chemical reactions, working down from the most energetic rung to the least, frozen at the exact point where it stopped. One researcher put a name to the whole structure: a fossilized chemical reaction. The reason that sequence matters is that it is the same sequence microbes climb. In lake beds and estuaries and river mud all over this planet, right now, there are bacteria eating organic matter by handing their spare electrons to iron. When the iron runs out, they hand them to sulfate instead. They do it for the same reason you ate lunch today. The transaction releases energy they can live on. The team wrote it up faster than anything in their careers. Submitted in November, 2 rounds of peer review with outside scientists trying to knock it down. It came out in Nature on the 10th of September 2025, and the language was as careful as language gets. A potential biosignature, something that might have a biological origin, and needs more evidence before anybody says either way. Read what that caution is actually admitting. The team searched the literature for an experiment in which somebody made vivianite this way without biology, and they could not find one. I think somebody probably will, eventually, because rusty iron and organic matter are famously reactive. The greigite is the hard one. Nobody has ever watched that reaction happen in cold natural conditions, without something alive driving it. NASA has a formal staircase for exactly this situation. 7 steps from first flicker to certainty. Spotting something odd gets you onto it. Proving the signal did not come off your own spacecraft moves you up. Showing the setting could plausibly have hosted life moves you up again. And then comes the step that has stopped everything we have ever found, ruling out every known way of producing that signal without life. Sapphire Canyon sits one step below it. The lead author's description of where his team stands is that they have started lifting a foot toward that step and have not put it down yet. One voice on that same paper deserves to be heard, because it belongs to a man who has spent his career pointing cameras at Mars. Jim Bell, a co-author, put the honest counterweight on all of it. It could indeed just be a coincidence. He is right, it could. Hold both halves of this at once, because it is a strange place to be standing. We have a rock that looks more like biology than anything we have ever pulled off another world. We have a formal process telling us we cannot know without a laboratory here on Earth. We have the sample already drilled, already sealed, already lying out on the Martian surface with its serial number and its name. All of it would be the greatest scientific triumph of our lifetimes, if not for one thing. Even if Sapphire Canyon turns out to be full of dead Martians, that by itself does not tell us what we need to know. Life on Mars might not be a second beginning at all. It might be a relative. Before we get to why that word should frighten you, there is a smaller question sitting underneath it, and almost nobody asks it out loud. Suppose the tube came home tomorrow. What would we actually do with it? The answer is that we would weigh atoms. Every element comes in slightly different weights. Carbon, sulfur, iron, all of them exist as versions with a few extra neutrons riding along. Chemically, the versions behave the same. Physically, the heavier ones are just a little more sluggish, a little harder to push through a reaction. Life notices. Living cells run millions of tiny chemical transactions a second. Across all of them, they consistently take the lighter version because it costs marginally less energy to move. Nobody decides this. It falls out of physics. Over billions of transactions, it leaves a bias in the leftovers, a fingerprint written in nothing but weight. You do the same thing without thinking about it. Given two identical suitcases, you take the lighter one every time. After 1,000 trips, somebody could work out which case was yours from the wear on the handle. That fingerprint is the test. We argue this way about the oldest rocks on our own planet. The 3.5 billion year old ones, where nothing is visible and everything is inference. When a geologist wants to know whether something alive was involved, they go to the isotopes. And Chayava Falls happens to be almost perfectly built for it. Because the iron in the mud and the iron inside the greigite are connected by a single reaction, you can compare them directly. Same for the sulfur, sitting in the leopard spots and in the mud around them. Same for the carbon, which is present in more than one chemical state in the same rock. 3 independent systems, 3 separate answers, all from one core. If all 3 point the same direction, and if that direction matches the offsets biology produces on Earth, then the story becomes very hard to argue with. None of that can be done on Mars. The instruments are the size of rooms. They need shielding, cryogenics, technicians, calibration standards, and the ability to run the same sample 40 different ways over 5 years. You cannot fly a room to another planet. So everything, all of it, the whole question, comes down to whether that rock ever leaves the ground it is standing on. Hold that thought. It comes back at the worst possible moment. Now the harder problem, the one that turns a triumph into a warning. Imagine the sample comes home, the isotopes line up, and the verdict is unambiguous. Something lived in that mud. Congratulations, we have found life on Mars. We would still not know whether we had found anything new. Here is why. Go back to the 400 pieces of Mars sitting in drawers on this planet. Nobody flew out and fetched them. An asteroid hits Mars hard enough to throw debris past escape velocity. That debris drifts around the Sun for a few million years. Eventually, some of it runs into us. This has been happening continuously for the entire history of the solar system. 2 houses on the same street during a hurricane. Roof tiles from one land in the other's garden. Year after year. For 4 billion years. After a while, asking which house something came from stops being a simple question. And now the detail I asked you to keep from earlier finally does its work. researchers reconstructed the temperature history of the Allen Hills rock, the one that spent 16 million years in space before hitting Antarctica. Through the whole journey, its interior stayed cooler than a warm bath. An impact blasted it off a planet. It sat in vacuum and cosmic rays for longer than our genus has existed. It hit Earth at enormous speed, and the inside never even got hot. Bacterial spores survive worse than that in a laboratory freezer. Which means the transfer route is not a theory. A documented delivery service runs in both directions, and has been running since before either planet had a solid surface. So there is a real possibility that Martian life, if it exists, is family. Same origin, same chemistry, moved between two worlds by rocks. Under that scenario, the great filter argument goes quiet. Finding your own cousin somewhere else tells you nothing about how easy it is to start a family. Life would have begun once in this solar system and then hitchhiked. One origin, same odds as before. Nothing learned, nothing lost. Keep that comfortable version in mind for about 30 more seconds. A group of researchers thinks the traffic mostly ran the other way. Joseph Kirschvink and Benjamin Weiss have argued it. Paul Davies has argued a version of it too, with the mathematics attached. The reasoning is uncomfortably good. Early Mars was smaller, so it cooled faster and settled down sooner. It had standing water while Earth was still being resurfaced by giant impacts. Some of the chemistry that Origin of Life researchers most want involves boron, molybdenum, and cycles of wetting and drying. That works better on a dry world with shallow ponds than on a planet drowned in ocean. Mars may have been the better cradle, and the delivery service runs downhill toward the Sun far more easily than it runs outward. Follow that through and you arrive somewhere genuinely strange. You would not be an Earthling who found life on Mars. You would be a Martian who found the ruins of home. And you would be standing on the only one of the two that still works. That is what Mars actually is, in the coldest possible reading. A planet where the experiment started, ran for a while, and then the room it was running in stopped being a room. Rivers, lakes, a thick enough atmosphere to hold them, then the magnetic field faded, the solar wind went to work, the air thinned, and the water went underground, or into space. The wettest stretch may have run for several 100 million years, and the outer estimates push it toward 1 billion. Then it closed. Nobody did that. There was no war and no mistake. A planet that size simply cannot hold on to its air for the length of time it takes to build something interesting. Call that a filter of a different kind. It says nothing about probability, which is what Hanson's argument is actually about. What it says is that habitability is a phase a planet passes through, and phases end. One test cuts through all of this, and it explains why the sample matters far more than the announcement did. Suppose the biology in that rock uses the same genetic code we do. Suppose it uses the same amino acids, turning the same way. In that case, it is a relative, and we have learned almost nothing about the universe. If it runs on something else, on chemistry that never appears anywhere in our own tree, then life started twice in a single solar system. Twice in one ordinary star system, around one ordinary star. If that is true, life stops being a miracle. Life becomes what wet rock does when you leave it alone, and every argument about our future changes shape in the same instant. To see why, you need the shape of the filter argument clearly in your head. The wrong version is easy to reach for, and far less interesting. Nothing in it depends on aliens being hostile, or hiding, or uninterested in us. It depends on exactly 2 observations, and you can check both yourself. The first is that we exist. Something went from dead chemistry to a species that builds radio telescopes, at least once, right here. The second is that when we look outward, nothing else appears to have done it. No engineered structures, no leaked transmissions. No sign that anybody has rearranged anything on a scale we could notice. Put those together and you are forced into a conclusion whether you like it or not. Somewhere along the road from bare rock to galaxy-spanning civilization sits a step of terrible improbability. The universe has run that experiment on an unimaginable number of worlds. Almost everywhere, it came up empty. The total difficulty is fixed by what we see. Most people miss that part. The sky sets the number. All we get to argue about is how that difficulty is distributed along the road. And that is where the whole thing turns personal, because the difficulty has to add up. If you prove that one early step is easy, that step can no longer carry the weight. The required improbability does not evaporate. It gets pushed onto whatever steps remain. Every piece of good news about the past is a debt transferred to the future. Which brings us to the first candidate, and to a result from 2024 that made a lot of people quietly uncomfortable. For most of the last century, the obvious answer to where the barrier sits was the beginning. Getting from chemistry to something that copies itself and evolves seemed like the hardest thing in the story. We still cannot do it in a laboratory. It felt like the perfect filter, safely behind us, and it let everyone sleep. Then, a team at the University of Bristol went looking for the age of our common ancestor. Every living thing on this planet descends from a single population of cells. Every bacterium, every mushroom, every whale, every person. Biologists call it the last universal common ancestor, and everything else branches off that trunk. By comparing genes that were duplicated before that split and counting mutations against known fossil dates, the team put a number on when it lived. 4.2 billion years ago. Now put that beside the age of the planet. Earth formed about 4.5 billion years ago. It was struck by something the size of Mars and had to reassemble itself and grow a moon. It stayed hostile for a long time afterward, and there is a real argument about when the surface could first hold liquid water at all. The pot had barely finished cooling and the water was already boiling. And what was in the water was not simple. The reconstruction suggests our common ancestor already had a genome of a couple of thousand genes and a working metabolism. It also carried the beginnings of an immune system, which tells you something bleak and wonderful at the same time. 4.2 billion years ago, our ancestor was already in an arms race with viruses, which means it was not the first thing alive. It was a late survivor of an ecosystem that already had winners and losers in it. Last April, the astronomer David Kipping ran the numbers through a framework designed to strip out the obvious bias in this kind of reasoning. The bias is real and worth naming. If producing observers takes billions of years, then only planets where life started early will ever have observers on them. So an early start might be a selection effect, rather than evidence of anything. His earlier work, using the oldest microfossils, gave odds of about 3 to 1 that life gets going quickly on Earth like worlds. Suggestive, below the threshold anybody would call strong. With the new date for our common ancestor, the odds crossed that threshold for the first time. Roughly 13 to 1 in favour of life starting fast. His own caveat is the important half of the sentence, and it deserves to be said as clearly as the headline. Life may start easily in Earth-like conditions, and Earth-like conditions may themselves be extremely rare. Still, look at what just happened to the argument. The most comfortable candidate for a barrier behind us, the one everybody reached for first, just got weaker. Origins look fast, and the improbability that has to exist somewhere just slid forward, closer to where we are standing. A serious counterweight sits here, and it comes from someone who has spent decades on the problem. Paul Davies points out that every other candidate step at least has a known mechanism behind it, which is Darwinian evolution. The origin of life has no known mechanism at all. Nobody can describe the process by which chemistry became biology, and you cannot calculate the odds of a process you cannot name. Fair point, and an honest description of where things stand. What we have is a suspicion built on timing, not a demonstration. So the barrier slides forward, and the next place it can hide is a stretch of time so uneventful that geologists have a nickname for it. Life shows up almost immediately, and then, for roughly 2 billion years, nothing much happens. Bacteria and their relatives run the planet. They invent photosynthesis, poison the atmosphere with oxygen, survive it, and settle into a very long, stable middle age. No animals, no plants, no fungi, just microbial mats and slime and stromatolites, for a stretch of time longer than the entire history of complex life since. Then, once, a single event happens that never happens again. One cell ends up living inside another one. An archaeon and a bacterium, permanently fused, one running its metabolism inside the other's body. That inner partner became the mitochondrion. Every organism on Earth with a nucleus, every single one, from an amoeba to the readers of this sentence, descends from that one merger. This was no ordinary acquisition. Two organizations with incompatible internal systems ended up as one company. One of them operates entirely inside the other's building, keeping its own rulebook and its own copy of the records. It should have failed. Mergers like that fail constantly. Nick Lane at University College London has spent his career on why it worked and why it seems to have worked only once. His argument runs on energy. A bacterium generates power across its outer membrane, which means the bigger it gets, the worse its power to size ratio becomes. The thing is stuck. Swallow a partner that brings its own membranes and its own power plants. Suddenly, a cell can afford a genome tens of thousands of times more expensive to run. That is the moment complexity becomes affordable. Everything you think of as a living thing happens downstream of it. Lane's position, stated in an interview earlier this year, is about as clean a version of the filter as you will find from a working biologist. He thinks early life is close to chemically inevitable and could be blooming on hundreds of millions of worlds in this galaxy alone. And he thinks the real bottleneck is the complex cell. Notice what that would mean if he is right. It would be good news. Genuinely good news. The barrier would sit 2 billion years behind us, and we would already be through it. A Mars full of ancient microbes is exactly what a universe like that should look like. Bacteria everywhere, nothing else anywhere. A cosmos full of pond scum and silence. You could live with that. I could live with that. Except that last year, 4 researchers published a paper arguing that none of it is hard. February of 2025 in Science Advances. Daniel Mills at the University of Munich with Jennifer McAlady, Adam Frank and Jason Wright. They took the whole framework, the coincidence Carter spotted, the hard steps, all of it, and went after the foundations. Their case rests on 2 ways that an ordinary event can disguise itself as a miracle. The first is that evolution destroys evidence. Deep time is not a filing cabinet. Lineages go extinct without leaving a trace, and after a couple of billion years, the record is mostly gaps. Something like the origin of complex cells might have happened several separate times, with only one line surviving to be counted. There are fossils from that era that look vaguely eukaryotic and cannot be tied to anything living today. They might be the wreckage of other attempts. The second is sharper, and once you see it, you cannot unsee it. Evolution has a winner-takes-all quality. The first lineage to pull off a new trick occupies the space that trick opens up, and it shuts the door behind it. Nobody else gets a second run at the problem, because the niche is already full. So an event can look unique for a reason that has nothing to do with being unlikely. It looks unique because it happened, and happening is what made a repeat impossible. Then they turn to Carter's original puzzle, the timing, and they offer an answer so ordinary it is almost insulting. We are late because the planet was not finished. Humans need oxygen, and not a trace of it. We need it thick, and by the geological record, that concentration was not stably established until around 400 million years ago. Mills puts the consequence plainly. For more than 9/10 of Earth's existence, there was probably too little oxygen in the air for people to live here for long. The steps that look like miracles all require an oxygen-rich world. Complex cells need the energy. Animals need more of it still. And the world only became that way because earlier life spent billions of years making it that way. You cannot launch the boat before the tide comes in. The tide took 4 billion years. Measured from the moment conditions actually permitted us, our arrival was not slow at all. It was prompt. And now the third thing I asked you to hold comes back. That physicist in London, with the overrunning talk and the unreadable slides, had handed the field a framework. It shaped 40 years of thinking about our place in the universe. Nobody in that room could follow it. The first serious, sustained assault on its foundations arrived 4 decades later. Notice what that quietly concedes about how much of this we have actually nailed down. Because this is a live argument, not a settled one, and the other side has good people on it. Andrew Watson at the University of Exeter agrees that Carter's model ignored environmental delays and has been working on a version that folds those delays in. He thinks the hard steps framework survives. Michael Wong at the Carnegie Institution was asked to referee. He said the new paper does not make a slam dunk case, but is probably as good as anyone can manage on the available evidence. Watson also did the thing that makes this science instead of philosophy. He named a prediction that could prove him wrong. If hard steps are real, we will eventually read the atmospheres of Earth like planets around other stars, and we will find only the signatures of a young, simple, microbial world. No oxygen-rich air, no complex biospheres. And he expects that verdict to arrive sometime this century. So look at the ledger for a moment. Origins, probably fast. Complex cells, possibly not hard at all. Multicellular bodies, oxygen, intelligence, all defensible as slow rather than improbable. Somebody used to point to each of those and say, there it is, the barrier, the reason the sky is quiet, safely behind us. And if all of them fall, the improbability does not go away. It cannot. What we see when we look up has already fixed it. It just has nowhere left to sit except in front of us. Here I want to be careful with you. It would be easy to spend the next 10 minutes being frightening and dishonest at the same time. Let me give you the facts as they stand, without decoration. On the 27th of January this year, the Bulletin of the Atomic Scientists moved the doomsday clock to 85 seconds before midnight. The clock has never been set closer. Not once since it was created in 1947, and not at any point during the Cold War. 9 days later, on the 5th of February, the last treaty limiting the strategic nuclear arsenals of the United States and Russia expired. It could only ever be extended once, and it had been. No replacement was agreed. The astrophysicist Daniel Holz chairs the board that sets the clock. He said that for the first time in more than half a century, nothing prevents a runaway arms race. The Secretary General of the United Nations issued a statement the same day, calling it a grave moment. The world now has no binding limits on the arsenals of the 2 countries that hold most of the weapons. Those are not predictions. Those are dates on a calendar that has already happened. Separately, the philosopher Toby Ord spent years assembling estimates of how likely it is that our species suffers an unrecoverable catastrophe this century. His figure is roughly 1 in 6. Russian roulette, in his words, with 100 years in the chamber. I want to be exact about what that number is and is not. His figure is a considered judgment from a careful person who shows his working. He says openly that reasonable people land an order of magnitude away in either direction. It is not a measurement. Nobody has run this century 1,000 times. And now the part that should actually keep you up at night. The arsenals are the smaller problem. For any of this to function as a great filter, it has to work almost everywhere. Not on us specifically, on everyone. On species with different biology, different politics, different histories, different everything. On billions of worlds, across billions of years. With a failure rate close to total. Nuclear weapons do not obviously clear that bar. They came out of one particular arms race between 2 particular nations at one particular moment. You can easily imagine a civilization that never built them, or built them and never came close to using them. A real filter would have to be something else. Something that every species discovers because it lies directly on the path that intelligence takes. Something that looks, from the outside, like the obvious next step. A door that everyone who gets this far opens, because from where they are standing, it appears to lead somewhere better. And here is the sentence I've been walking toward for the last hour. We do not know what that door is. And that is the actual state of the science. Not a warning about a specific technology. An empty space in the argument, exactly where the explanation should be, and every candidate we can name looks too parochial to fill it. If the barrier is ahead of us, we cannot currently see it, which is, on reflection, precisely what you would expect from something that catches everybody. Alright, breathe. Because there are several perfectly respectable ways out of this, and you deserve to hear them properly rather than as a footnote. The first is that the paradox may not exist. In 2018, Anders Sandberg, Eric Drexler, and Toby Ord went back to the equation everyone uses to estimate how many civilizations are out there. They pointed out a basic error in how it has always been used. People plug in a single best guess for each unknown and multiply, but several of those unknowns are not uncertain by a factor of 2. They are uncertain by many orders of magnitude. Carry that uncertainty through the calculation honestly, using ranges instead of single guesses, and the answer changes character completely. Their result was that a silent sky is not surprising at all. On their analysis, we are more likely than not alone in this galaxy, and there is a substantial chance we are alone in everything we can see. Where is everybody? Probably very far away, and quite possibly beyond the edge of the observable universe, forever out of reach. No filter required, no looming doom, just an empty neighbourhood and bad statistics. This result has been challenged in print, and the challenge is specific. Critics have argued that the conclusion depends heavily on how they handled one particular unknown, the probability of life getting started. Treat that term differently and the answer shifts. The disagreement has not been settled. Roughly where everything in this field lives. The second exit is simpler, and it is my favourite, because it is about humility rather than mathematics. Jill Tarter and her colleagues, and later Jason Wright with Shubham Kanodia and Emily Lubar, tried to quantify how much of the search we have actually completed. The question was not how many stars we have pointed at. The question was how much of the whole space of possibilities we have covered, every direction, every frequency, every signal strength, every moment in time when something might have been arriving. Their answer is a published calculation rather than a figure of speech. All of our radio searching so far amounts to roughly a hot tub's worth of water, drawn from every ocean on Earth. You look into a hot tub, there is no dolphin in it. You would be an idiot to conclude that dolphins do not exist. Our position, honestly stated, is that hot tub. The great silence might be nothing more than the sound of us barely having started. The third exit is a story from last year, and it is the most useful of the lot, because it shows the machinery working. In 2023, a team using the James Webb Telescope reported a tentative signal. It came from the atmosphere of a planet called K2-18b, about 120 light-years away. The molecule was dimethyl sulfide. On Earth, essentially all of it is made by marine plankton. The headlines wrote themselves. In 2025, the same group came back with new mid-infrared data and a stronger claim. The coverage was enormous. Then other teams got hold of the raw observations. They reanalyzed the near-infrared data using multiple independent pipelines and hundreds of different model fits, and could not recover the signal. They found the mid-infrared measurements were badly sensitive to instrument systematics, so that different reasonable choices about how to bin the data produce wildly different planets. By the beginning of this year, the evidence for that molecule had essentially evaporated. Nobody lied, nobody cheated. A claim was made, the community stress tested it, and it did not hold. The immune system of science functioned exactly as designed, in public, on a 2-year timescale. Keep that in mind when anybody, including me, tells you what a rock on Mars means. Which brings us to the most quietly reassuring fact in this entire video. In June of this year, a group of researchers did something obvious that almost nobody does. Instead of quoting 3 experts, They surveyed hundreds of astrobiologists from across the global research community. They did it within days of each announcement, and they asked one simple question. Do you think extraterrestrial life has probably been found? For the exoplanet, out of every 100 astrobiologists, only about 7 said yes. The clear majority disagreed outright. For the Martian rock, confidence was higher and still cautious. About 15 in every 100 said yes. Most of the rest had moved into the middle, neither agreeing nor disagreeing. The people who understand this evidence better than anyone alive are, on balance, calm. But calm is not the same as unconcerned. And one more fact about that sealed tube in Jezero Crater has nothing to do with chemistry or philosophy or the age of the universe. It is a fact about a budget. On the 8th of January this year, the House of Representatives passed a spending package for the federal government. Buried inside it, in the section covering NASA, was a short passage of plain administrative English. The agreement does not support the existing Mars sample return program. That sentence ended it. Not a vote about aliens, not a debate about the Great Filter, a line item. I want to be precise here, because the easy version of this story is wrong. NASA was not gutted. The bill funded the agency at roughly $24 billion, rejecting most of the deep cuts that had been proposed a year earlier. Planetary science survived. What did not survive was the mission designed to go and get the rock. Congress moved about $110 million into a new technology program so that the engineering work would not be thrown away. Landing systems, entry and descent, the hard problems of putting something heavy onto a thin atmosphere. Useful work, and none of it is a spacecraft. The chair of the group that advises NASA on Mars exploration said the community was deeply concerned. Sample return had been the single highest priority in the last 2 decadal surveys. Those are the reports the national academies produce every 10 years to tell the country what matters most in space science. Twice in a row, the field's own experts put this mission at the top of the list. Across the Atlantic, the European Space Agency had been building the Earth Return Orbiter at Airbus in Toulouse. That vehicle was supposed to catch a container in Mars orbit, autonomously, something nobody has ever attempted at another planet, and carry it home. Europe is now reconsidering its Mars plans entirely, and the practical consequence sits on the ground in Jezero Crater. More than 30 sealed tubes laid out on the Martian surface with no approved plan to retrieve them. The rover is still working, still filling the last of its empty tubes. It has no way to bring anything back. It never did. That was always somebody else's job, and that somebody is currently nobody. Think about what those tubes are. Somebody chose the rock. Somebody drilled it, sealed it, and set it down where a future spacecraft could find it. There is a letter written, addressed and sealed, lying on the doorstep of another world, and the postal service has been shut down. The lead author of the Nature paper put the stakes about as simply as anyone could. The answer to whether life ever existed on a world other than this one might be inside that little tube. The host of the Planetary Society's radio program said the thing everybody in the field is feeling. It kills her that the samples are just sitting there, waiting. Now, that is not the end of the story, because the tubes are not the only samples in play. China's Tianwen-3 mission is going to Mars, and it is not going there to look at rocks. The plan is to bring some home. The plan calls for 2 launches around the end of 2028 on separate rockets. A lander goes down, collects material, and fires it back into Mars orbit. An orbiter catches it and carries it to Earth. The target for the return is around 2031. They intend to bring back no less than 0.5 kilogram of Martian material, roughly the weight of a paperback book. And this is the part that gets overlooked. Searching for signs of life is not a side objective for Tianwen-3. The mission plan lists it among the primary scientific goals, and the team has published the details in the literature. They are building a dedicated high-security laboratory to receive the material, with ultra-clean rooms and biosafety areas. The return samples will go through sterilization and a formal biological risk assessment before anybody studies them properly. Earlier this year, the mission moved into flight model development. Site selection has narrowed from more than 80 candidate landing zones down to 19, with 3 finalists due to be chosen before the end of this year. So the first Martian rock ever examined in a laboratory on Earth may well arrive in a Chinese cleanroom around 2031. Chosen by a mission designed from the start to look for life in it, which would mean the answer arrives, just not from the rock we already know is interesting. And there is one more piece of arithmetic worth putting in front of you, because it is the quietest and possibly the strangest fact in this entire story. For 2 decades, in one form or another, the astronomy community has been designing a telescope. The current name is the Habitable Worlds Observatory. Its job description runs to a single sentence and reads as slightly absurd when you say it plainly. Find at least 25 potentially habitable planets around other stars. Photograph them directly. Read their atmospheres for oxygen and methane. That machine is the instrument that settles the argument we have spent this entire video having. Andrew Watson's prediction about only ever finding simple microbial worlds. The question of whether oxygen-rich biospheres are common or vanishingly rare, whether the hard steps are real, all of it becomes an observation instead of a debate. Congress funded it last year at about $150 million. The following year's budget request asked for $5 million. Read that again, slowly. From 150 to 5. Nothing has been cancelled. Design work continues, contractors are still developing the ultra-stable optics, and the community is still holding its conferences. But the funding line for the only instrument that could answer the question directly went down by a factor of 30 in a single year. Put the 2 facts side by side, and something uncomfortable emerges. The sample that might contain the answer is lying on Mars, with no ride home. The telescope that might contain the answer is being slowed to a crawl. Neither decision was made by anyone thinking about the Great Filter. Both were made in rooms where the subject was money. Perhaps the strangest thing here has nothing to do with the answer destroying us. We appear to be walking away from it for reasons of accounting. So let me tell you plainly what happens if we do get the answer, and it comes back the way the filter argument fears. Suppose the isotopes line up. Suppose the biochemistry turns out to be alien, running on a genetic system that appears nowhere in our own tree of life. That would mean the universe started life twice, independently, in one ordinary star system. 2 separate beginnings within a few 100 million years of each other. At that point, the rarity of life stops being available as an explanation for the silence. You cannot say the sky is quiet because life is hard to start. We would have just watched it start twice, next door, on a planet that is smaller, colder, drier, and worse in every measurable way than this one. If it happened on Mars, it happened on billions of worlds. So the quiet needs a different explanation, and there is only one place left to put it. That is the whole argument. It is not mystical, it is subtraction. A second piece of evidence points the same way, and it arrives from an unexpected direction. Not biology, timing. In 2021, Robin Hanson and 3 colleagues published a model in an astrophysics journal asking a simple question. Take how stars form, how long planets stay habitable, and the assumption that reaching our level takes some number of difficult steps. When should a species like us expect to show up? Their answer is that we are early. Not slightly early, extraordinarily early. Under most reasonable settings, the overwhelming majority of advanced life in the universe should arrive after this moment. Small red stars burn steadily for hundreds of billions of years, far longer than the sun will. If getting complicated takes a long time, then most civilizations should emerge in the deep future, around those small stars, ages after our own sun has died. Yet here we are, near the beginning, orbiting a short-lived yellow star, in a universe that has barely started. Hanson's proposed explanation is uncomfortable. He suggests there is a deadline. If expanding civilizations eventually claim the volume of the universe, then anybody appearing late appears inside somebody else's territory. They never get to be an independent beginning at all. The only species who get to ask these questions are the ones who arrived before the doors closed. Fit that model to the data, and you get a picture in which such civilizations already hold a large fraction of the universe. On those numbers, we might meet one within a couple of 100 million years. Let me flag clearly that this is a model with assumptions bolted onto assumptions, and serious people have attacked it. The astronomer David Kipping has raised two objections. The first is that the model needs those small red stars to be habitable, and the evidence on that is currently going the wrong way. The second is sharper. The model leans on expanding civilizations travelling close to the speed of light, which conveniently explains why we cannot see them, and which no experiment could ever falsify. Both criticisms are fair, but the puzzle Hanson is trying to solve does not disappear just because his answer might be wrong. We appear to have shown up early. Something has to account for that, and most of the available accounts involve the future being far less open than it looks. And now the part that makes this different from every other cosmic horror story you have heard. This one has a schedule. The European rover Rosalind Franklin is scheduled to launch in 2028 and land in 2030. It carries a drill that reaches 2 meters down, deeper than anything ever sent to Mars. Radiation sterilizes the top layer of that planet, so anything delicate survives only underneath. Its onboard laboratory is sealed and sterile, built specifically to look for the molecules life leaves behind. Tianwen-3 brings material home around 2031. If Mars sample return is ever revived, the American samples follow in the mid to late 30s. Which means this is not a question for your descendants. If you are watching this and you are under 60, there is a reasonable chance you find out. The verdict on whether the universe makes life easily, and therefore on where the barrier most likely sits, may land inside your working life. An extraordinary thing to be able to say. And it is why the argument stopped being philosophy. Now let me do the honest part, because a scary argument that cannot be attacked is not an argument at all. The filter reasoning rests on 5 load-bearing joints. Break any one of them, and the whole structure comes down. 3 of them you have already met tonight, so I will only name them. The sky may not be empty, because we have barely searched it. Martian biology may be our cousin rather than a second beginning. And the statistics may dissolve the paradox outright, leaving nothing that needs explaining at all. The 4th joint we have not touched, and it is the most technical and the most important. The argument assumes the barrier is one wall. It might instead be a long series of low fences. 50 steps, each one of which most travellers clear and some do not, multiplying out to the same terrible number without any single step being impossible. In that version, there is no dramatic filter waiting for us. There is just a long road with attrition, and we are somewhere on it, and the odds are what they are. A 5th joint sits underneath the other 4, quieter than any of them. The whole argument takes for granted that a sufficiently advanced civilization expands, visibly, across a galaxy. A claim about motivation made by a species that has never sent anything living beyond its own moon. Perhaps what happens to civilizations is that they get small and efficient and interested in things we cannot imagine and stop needing more room. From here, that would look identical to extinction. Any of those could be true. Several could be true at once. What none of them do is make the question go away. Because whichever version is right, we remain the only known instance of the process. We are running the experiment in real time, and we do not get to see the results of anybody else's run. Step back from Mars for a moment, because the solar system has become a much more interesting place while we were arguing. Saturn's moon Enceladus is a ball of ice, about as wide as Iceland is long, and it leaks. Through cracks near its south pole, it sprays water from a hidden ocean straight into space. In 2008, the Cassini spacecraft flew through that spray at nearly 18 kilometers per second, its fastest pass through the plume. Its dust analyzer was struck by ice grains that had been ejected minutes earlier, around 20 kilometers above the surface. Space had not yet had a chance to alter them. Nobody could fully read that data at the time. Cassini stopped transmitting in 2017 when it was deliberately flown into Saturn. Last year, a team in Berlin went back to those old spectra with better methods and published the results in Nature Astronomy. Those minutes-old grains carried a range of organic compounds, and several classes of them had never been identified in Enceladus material before. Not weathered fragments from the ring system. Fresh chemistry, coming straight out of an ocean nobody has ever seen. Combine that with the phosphates found in the plume a couple of years earlier, and you reach a strange milestone. Life on Earth is built from 6 elements. 5 of them have now been detected in material coming out of a small moon most people cannot find on a diagram. Then there is Europa, which is the one that keeps planetary scientists awake. Under an ice shell of unknown thickness, Jupiter's moon probably holds more liquid water than every ocean on Earth combined. In October of 2024, NASA launched the heaviest planetary spacecraft it has ever built to go and look at it. Europa Clipper is out there right now. On the 3rd of December this year, in a few months, it will swing past Earth for a gravity assist, close enough that it passes over your head. After that it heads outward, arriving at Jupiter in April of 2030, where it will make 49 close passes over that ice. In 2028, a nuclear-powered drone called Dragonfly launches for Titan, Saturn's largest moon. It will fly between sites in an atmosphere thicker than ours, over dunes of frozen organic material and lakes of liquid methane. Even Venus refuses to stay quiet. Astronomers have reported 2 gases in its clouds, phosphine and ammonia, which on Earth are made overwhelmingly by biology or by industry. The detections have been fought over bitterly for years. One of the leading researchers was asked for his own honest estimate. He gave odds of roughly 1 in 5 that it is life, and 4 in 5 that it is chemistry nobody has worked out yet. A scientist doing his job properly. More useful than any headline about aliens on Venus. And out past all of it, the exoplanets keep complicating the picture rather than simplifying it. The great hope of the last decade was a system called TRAPPIST-1, a small, cool star with 7 Earth-sized worlds, several of them in the zone where liquid water could exist. If red dwarfs like that are habitable, then the number of possible homes in this galaxy goes up enormously, because most stars are red dwarfs. The James Webb Telescope has now looked. The innermost planet appears to be a bare rock with no atmosphere at all. The spectrum of the 4th one, the world everybody cares about, is currently consistent with a flat line. Bare rock, or a heavy atmosphere, or thick cloud. Nobody can tell. The star flares constantly and contaminates the measurement. The habitable zone around a red dwarf may turn out to be a mirage. We do not know yet. Everything about this is unfinished, and that is the honest summary of the field in a single sentence. One more idea belongs in this picture, and it will change how you look at the ground. In 2018, a climate scientist at NASA and an astrophysicist at Rochester asked a deliberately provocative question in a peer-reviewed journal. If an industrial civilization had existed on Earth many millions of years before us, would we be able to tell? Their answer was uncomfortable. For anything older than roughly 4 million years, direct evidence would almost certainly be gone. Fossilization is rare. Exposed rock is a tiny fraction of the surface. Complex objects almost never survive. Even our own civilization would show up in future sediments, mainly as a chemical smudge. A spike in carbon and nitrogen, plus some strange synthetic compounds. And that smudge looks unnervingly similar to several natural events already sitting in the geological record. They were careful to say they were not claiming anyone was here before us. Their point was about detectability, and it lands hard. If a filter had already fired on this planet, somewhere in the deep past, we might be standing on the evidence right now, and be entirely unable to read it. Which brings the scale of our actual knowledge into focus. We have been listening to the sky for about 65 years, since the first deliberate search in 1960. Less time than a single human career. Our own radio emissions started leaking outward earlier than that, and by now they fill a bubble roughly 100 light years across. Our galaxy is 1,000 times wider than that bubble. We've announced ourselves to a sliver of our own neighbourhood, and we've been paying attention for the blink of an eye. A matching problem sits at the other end, which is how long anybody stays visible at all. We have been radio loud for roughly a century, and we are already getting quieter. Broadcasts that once blasted in every direction from enormous towers are moving onto fibre and onto tight satellite beams. They are becoming compressed digital signals that look like noise unless you hold the key. A civilization exactly like ours, a few hundred light years away, might be detectable for a window of 100 years. Then it fades back into the background, still perfectly alive, simply no longer shouting. Fold that in, and the silence gets cheaper to explain. You are listening for civilizations that happen to be loud, in your direction, at the precise moment your telescope is pointed there, and using a technology you thought to check a far narrower target than simply listening for civilizations. None of which proves anybody is out there. It only means the emptiness we keep citing as evidence may be a much weaker observation than it feels like when you are standing under it at night. On that evidence, we are drawing conclusions about the fate of intelligence in the universe. So let me go back to the question we started with, because it has changed shape while we were talking. The question everybody thinks this field is asking is, are we alone? It never was. That question is answerable only in one direction, and it has no consequences either way. Finding company would be wonderful. Finding nobody would be lonely. Neither one tells you anything you can act on. The real question, the one that has been sitting underneath this whole time, is different and much less comfortable. How much time does something like us usually get? And is there anything that determines it other than luck? That is what the tube in Jezero Crater is actually about. This was never a search for company. This is a survey of how often the universe manages to do this, which is the same as asking how often it fails, which is the same as asking what our odds look like. And here is what I keep coming back to, at the end of all of it. Whatever is in that rock, the fact that we can ask is the most remarkable thing in this entire story. Consider what had to happen. A planet cools. Chemistry becomes biology in some way nobody can yet describe. 4 billion years of copying errors and extinctions and ice ages produce, among 10 million other species, one that can look up. That species spends almost its entire history assuming the lights overhead are holes in a dome. Then, in about 400 years, it works out what stars are and what planets are, how old everything is, how the elements in its own body were made. And then it builds a machine, flies it across 300 million kilometers of vacuum, lands it inside an ancient lake bed, drives it to a rock chosen on the basis of color and texture, drills that rock, seals a piece of it in metal, and sets it down where somebody might one day come and collect it. We did that. Ordinary matter, briefly arranged into something that can wonder, sent part of itself to another planet. To check whether the universe had ever tried this before. None of that is consolation for the fear. It is the same fact as the fear, looked at from the other side. And there is one genuinely hopeful thing buried in the darkest version of all this. If the barrier is behind us, then we are extraordinarily lucky, and we can do nothing about it either way. The matter is already settled. The dice were thrown before anything existed that could care about the outcome. But if the barrier is ahead, then it is the only catastrophe in the history of catastrophes that is made of decisions. Not an asteroid, not a supernova, not the heat death of everything. If something reliably ends civilizations at roughly the stage we have reached, it is something civilizations do. Which means it has an address, it has a date, it has people with job titles and budgets and meetings. A horrifying thought and a strangely empowering one. And they are the same thought. And knowing would change what we do with the time we have. Bostrom drew the practical conclusion from this years ago, and it is deliberately unglamorous. If our species has any real chance of a long future, then anything that shifts the odds of that future outweighs almost everything else on the agenda. By orders of magnitude, because of how much sits on the other side of the scale. That sounds like an abstraction until you look at how we actually behave. Ord makes the comparison bluntly in his book. Every year, humanity spends more on ice cream than on making sure the technologies we are building do not destroy us. An argument that begins with a rock in a dry riverbed on another planet ends up somewhere very close to home. It ends up as a question about what a civilization chooses to pay attention to while it still has the option. You cannot argue with a gamma ray burst. You can argue with a decision. I'm not going to pretend I know which side of the barrier we are on. Nobody does. Anybody who tells you otherwise, in either direction, is selling something. What I can tell you is that the evidence exists. The evidence is sitting on a shelf, and we have not yet decided whether to go and read it. So picture it one more time as we finish. A crater on Mars about 45 kilometers across. 3.5 billion years ago it was a lake fed by a river. Mud settled quietly onto its floor, while Earth had nothing on it but bacteria. Today it is dust and rock, and a sky the colour of weak tea. The temperature drops far below anything you have ever stood in. Nothing moves except the wind. And lying on the ground, in a cylinder of titanium about the size of a marker pen, is a piece of that mud. Sealed, labelled, waiting. The tube is not going anywhere. It has no deadline. That tube will outlast every institution currently arguing about whether to collect it, and every person listening to this, and probably the arguments themselves. We always assumed that when we finally went looking for life beyond this planet, we were looking for company. We may have been looking for a warning the whole time. So I will leave you with the question I cannot answer, and I would genuinely like to know what you think. When that tube is finally opened, which result would frighten you more? Finding something alive in it, or finding nothing at all? Think about that before you answer, because your first instinct is probably wrong. If this changed the shape of the sky for you tonight, hit like and subscribe, and put your answer in the comments, along with one more. If the decision were yours to make, would you bring that sample home, or leave it exactly where it is? The universe has been quiet for a very long time. We are the part of it that finally started asking why.